Yeah, I think we can start it. Before starting today's session, today's seminar, I would like to make an announcement that this semester, several seminars are going to be held not in the physics department at the 10th floor, because the room has been booked by another professor. So please, in the next seminars, double check the room. Okay, so it is with a great pleasure that I introduce today's speaker. He's Massimo Passera. He's a professor in the University of Padova, a senior researcher for INFN, the Italian National Institute of Nuclear Physics. And he's an expert in precision calculations in the standard model of loop calculations. Today he's going to talk about the muon g-2 puzzle. He's also, since last fall, the director of the scientific office of the Italian embassy in Seoul. Today he's not going to talk about diplomacy. Today we talk about physics. So today we are going to hear about the muon g-2 puzzle and some new ways to disentangle a problem that has been going on for a long time. So please, Massimo, let's start.
Thank you, Stefano. Thank you very much. It's really a pleasure to be here. And I was telling Stefano, this is called my first talk with physics talk with a tie. And we have been talking about organizing this for some time, and finally we managed to organize. I'm very happy to be here at Sorbonne University. Thank you for the hospitality. So yes, I will talk about this muon g-2 puzzle. And as you will see, it's really a puzzle. In fact, there are probably several puzzles, and I will try to discuss them and see where we hope to go in the future. I would like to dedicate this talk to Professor Kinoshita. He just passed away last week, and Professor Kinoshita was a hero of our field. This is a picture of him computing the 5-loop contributions to the electron g-1, g-2. And you will see in the next few slides how much work he did over the years. He has been really, as I said, a hero of our field. Okay, so this is the situation. Yeah, on Zoom, I know you will not see the pointer, but it's not so crucial. Here you see the picture of the difference between elements on the right-hand side, the old one of the muon g-2 from Brookhaven, BNL, you see it here, and this one from is the result that we saw from Fermilab, and it confirmed very well the result from Brookhaven. You see them written down here. It's this is the experimental value from Brookhaven. This is the one from Fermilab, and this is the world average that we have today. Notice that Fermilab is only the first result that we have from Chicago. This is really the run one. And it's really just the beginning of the story. This is the 6% of the expected statistics from this experiment. So there is a lot of expectation for the upcoming results from this experiment at Fermilab. In fact, the new result from run 2 and the 3 will come in this summer, most likely this summer, and it will have an uncertainty reduced by a factor of 2. So it's already a big improvement. And you see, then the final goal of Fermilab is to go down to this uncertainty of 16 in 10 to the minus 11. You see, now we are at the level of 41 10 to the minus 11. Okay, so it's already a very, very precise number. As you can see, there are so many digits here, but we are really, the goal is really to go down to 16 in 10 to the minus 11. The first 5 runs are completed at Fermilab, and the 6th one is in progress right now. There is also another experiment in Japan at the J Park, and this experiment it's completely completely different, which is good because it will be complementary to the one of Fermilab, different method, completely different way of measuring this property of the muon, and it will start with a phase one uncertainty, which will be comparable to the one at Brookhaven. So this is the discrepancy that we have, or we had, let's put it like this, from the standard model prediction. Okay, and we're all excited about this muon g-2 because of this difference that you see here from the experimental average to the value that we had. When I write WP20, I mean this result that I will quote several times here is called the white paper. So it's a big booklet from the g-2 theory initiative, which puts together a lot of theorists. In fact, one over alpha, as if we were discussing at lunch. Almost one over alpha, and it's a number of physicists that with expertise in the standard model who did precision calculation and tried to come up with one single number, the standard model prediction. And as you see here, there is a tension of 4.2 sigmas. This is what we had at the time, but the situation has evolved, and you will see how the situation has evolved in the meanwhile. So let me start with the discussion, in fact, of the standard model prediction of the muon g-2. So first of all, a few definitions in order to be all on the same page. Here it is, a very, very short history of the topic. What is A? What is the anomaly? The anomaly is the G factor that you see here, G minus 2 divided by 2. Okay, in the Dirac equation, G is equal to 2, as you all know, but quantum electrodynamics in 1948, Schwinger, using QED, obtained this value, which is not 0. It is 0.00116 and so on. So it's alpha over 2 pi. It's a very famous result. And this very famous result was, in fact, in perfect agreement with the measurement of cushion Foley. You see, 0.1100119. And notice these two results, you see 116 compared with 119 with an uncertainty of 5. When I put the parentheses here, I, of course, mean 1 sigma uncertainty, the last digit. Okay? And, well, as you see, these are in perfect agreement. And this was an enormously important result. I mean, this was really the beginning of QED. People started believing in QED.
Sorry, by the way, the measurement is when it was
the same year, 1948. Yes, very same year. In fact, right afterwards, Schwinger did the calculation and he obtained this famous result. So it was really a turning point. 20 years later, essentially, after the Dirac equation. Great triumph for relativistic quantum field theory, which is QED, and essentially we keep doing this. We keep studying the interaction of the muon, okay, electron. For this term here, electron or muon doesn't make a difference, but later on, of course, it will, and I will tell you where. But here I put muon, but it would be the same as electron for this diagram. So we keep studying the interaction of the C. This is a photon, is the magnetic field interacting with the muon or electron. How do you parameterize this interaction term here? Here it is. This, we call it vertex. This vertex that you see here can be written in terms of form factors. You see here F1, F2, and there are others. F1 at Q squared equals 0, Q squared is transfer moment, squared momentum transfer, is the electric charge. It's electric charge in units of E, and you see there is an E here. Okay, the electric charge. So this is the charge. The second one at Q squared equal to 0 is exactly this A, the anomalous magnetic moment or anomaly. There are other form factors. They will give you the electric dipole moment and the anapole moment, but I will not discuss them in this talk. So, as a theorist, what we have to do is take your model, take the standard model or an extension of the standard model, and compute this form factor F2 at Q squared equals 0. That is your theoretical prediction that has to be compared with the experimentally measured value. Okay? Keeping in mind that the experimental precision is, let me go back here, this amazingly small number 41 in 10 to the minus 11. So as a theorist, you have to remember that if you want to make something useful, it has to be at this level of precision. Okay? If it's not this precise, you will not benefit from the precision of the experiment to make your comparison. All right, so this is what has been done, and the idea of what has to be done. And this is in one slide. I just really stick to one slide. This is the work from 1948 to very recently, the QED calculation of the muon g-2. By QED, I mean the subset of the full standard model, the subset of diagrams, Feynman diagrams of the full standard models that only contains leptons and photons. So QED, quantum electrodynamics. You see, in fact, here in this diagrams, you see this is the famous result diagram that gives the famous result by Schwinger. You see it here. This is one loop. You see there is one closed loop here. This is going to two loops. Already at two loops, there are a few more diagrams. It's not only one diagram. When you go to three loop, there are many diagrams. And then four loop and five loop. We're talking about thousands of diagrams. Okay. This is an enormous effort, and today is sometimes taken a little bit for granted because this has been done a few years ago with refinements, recent refinements, but still bulk has been done a few years ago. So people tend to forget it. But if we are able to talk about g-2 electron or muon, is thanks to the work of these people for decades. Okay, the first calculation was done in 48, and you see in the 50s was the first calculation of the two-loop contribution, then the three-loop calculation done by Remedi, Barbieri, Laporta, several people, and then the four-loop calculation, which is astonishing. And it actually was only completed in 2017 by Stefano Laporta analytically. He computed, I don't know how many diagrams, but I know that he quoted the results with 1,000 digits. And this is the five-loop contribution that the hero of this calculation is Laporta. It was Kinoshita that, as I told you, just passed away. And the diagrams that I showed you in the picture were, in fact, with this contribution. Now, you may ask, how many loops do I have to compute? I mean, are they all relevant? Is it to which level of precision do I have to go? Well, you saw it from the experiment. Now, how large are these things? Well, let's have a look at the four-loop. The four-loop contribution is 380 in 10 to the minus 11. I always use 10 to the minus 11, so it's easy to compare. Okay? The uncertainty is 4. Experimental uncertainty is 41. So, I mean, it's this value here, right? So really remember that we always have to keep in mind this 41 that you see here, all right? So the for loop is 380, so it's definitely very important, otherwise you could not do any comparison. But also the 5 loop is relevant. Well, it's not so relevant, it's 5, it's about 5. So the 5 loop contribution is not so crucial for the comparison nowadays. All right, so if you take all these coefficients that, as I said, you compute by doing the Feynman diagram calculation, then you multiply them to alpha over pi squared, cubed, 4th power, 5th power, and you get the standard, the QED prediction of the muon g-2. Of course, you need the value of alpha. Now, the value of alpha, you take it from somewhere else, and you take it from direct measurements. The one that I took here is the one taken by the Parker et al. Measurements in Berkeley, 2018. There is actually another measurement, another very precise measurement from Paris, from the Paris group, and the two are actually in disagreement. But this difference between the two, even if the disagreement is crucial, this difference is not important for the muon g-2. It's relevant, very relevant for the electron g-2, but not for the muon g-2. Okay, so I will not dwell on these details, but just keep in mind that for the electron g-2, the situation is complicated by the fact that you have two different measurements of alpha, and these two different measures of alpha, which are very different, they are more than 5 sigma difference away, they do not allow to do a test of the standard model.
So the 100 here is 0.1 times 10 to the minus 11, right?
Exactly, okay. Exactly. It's 10 to the minus 12. Yeah, the digits are given like this. So this is 10 to the minus 12 is the largest uncertainty due to the estimate of the missing next contribution, which is the 6 loop contribution. And actually, you have a shift, which is, you see also here, you have 10 to the minus 0.6, 10 to the minus 13, which is due to a slight difference that there is nowadays in a calculation of by Volkov of a class of diagrams, the class A110 no leptons, which is in disagreement with the result of Kinoshita. But again, it's a variance, but it's negligible, the difference, so I'm not talking about it. And it's all contained in this uncertainty here. So the QED contribution is really very good standing. It's very precise. It's not the place to look for discrepancy. when you compare with measurement. Now, let's go to I will not talk about the electron g-2, but if you want, at the end, we can discuss about it briefly. Now, the weak contribution is much, much smaller. It was computed in the 70s. These are the diagrams with the Z. You see there is an exchange of a Z here, and W, so there is a neutrino here. And this contribution is 195 in 10 to the minus 11. And then in the 90s, people started computing higher order. The two loop was computed. There are even higher order contributions that have been studied. And the result is this one here. 153.6 in 10 to the minus 11 with an uncertainty that is negligible. So again, negligible uncertainty, a very good solid result, no problems here. This uncertainty is really tiny and is due to these small hadronic contributions inside the weak contributions. You see there is a Z here. So these are weak contributions, but inside there are some hadronic parts and therefore they give a small uncertainty. But we will come to the hadronic uncertainty in the next slide. So again, for the weak contribution, no problem. And now we come to the hadronic contribution, which on the contrary is the problematic one. You see, the leading one, the most important hadronic contribution is the one that you see here. So it is the usual Schwinger diagram that you see here, but now you insert in the photon here, in the photon propagator, you insert a vacuum polarization. Okay? So you understand right away that this is how do I compute this, because it's what we were chatting before, right? I mean, how do I compute this term? I cannot use perturbative QCD. Here I have all momenta, it's a loop integral. And well, the solution was actually thought decades ago. We know the analytic properties of this function here, this vacuum polarization. So we actually know that we only need to know the imaginary part of this vacuum polarization. And the imaginary part, because we can relate to find the rest with the dispersion relation. And actually, the second step is that to know the imaginary part, we just need to use the optical theorem and measure it. We can measure the cross-section of E plus, E minus into a final state made up of anything contained in this bubble. And anything contained in this bubble is hadrons. So you have to measure E plus, E minus, the cross-section sigma that you see here, the cross-section of E plus, E minus into hadrons. And from that, you get the imaginary part, and as I said, you get the full contribution. This is the expression that is normally written, so you need to do this integral, where this is a known kernel function. It's written here in integral form, just because it's a bit lengthy if you write it in the integrated result. But this is the kernel function, and this is the experimental input that you have to use. So please do not be confused. We are talking about the theoretical prediction. Okay, the theoretical prediction for the muon g-2, but to do this theoretical prediction, we are using some experimental input. And this experimental input is the cross-section, the hadronic cross-section of E plus, E minus into hadrons. Now, where should you measure this cross-section? Well, you see it here. We need it from the threshold, pi 0, mass of the pi 0, up to infinity. Okay? But actually, the weight function that you see here, this kernel function k, gives a lot of weight at low energy, roughly goes like 1/s. So it really matters very much, and you see the pie chart here. This is the total contribution, 100%. But as you can see here, from the pion mass to 0.6 GeV, you already have this contribution. By 1 GeV, you already have all of this green contribution. And then you see the rest is very small and smaller and smaller. So you really have to measure this hadronic cross-section at low energy. And you have to measure it very precisely because you want to have this result precise. How much precise? Well, you see here. These are results obtained in the latest determination. The one that you see here is the white paper value. See, WP20 is the white paper value. As you see, this value is about 7,000 in 10 to the minus 11. So you needed to know with a precision which is better than 1%. Because remember, we need 40, the experimental value has an uncertainty for the muon g-2 has an uncertainty of 41 in 10 to the minus 11. Okay? So we need to compete with that. And in fact, this result, as you see, has the same, practically the same uncertainty, 40 in 10 to the minus 11, which means that you are knowing this value with a precision of better than 1%. Okay, this is not easy. You can imagine this because you're doing, we're talking here about low energy hadron physics, E plus E minus into hadrons, measured with precision below 1%. Okay, so very, very precise measurements. Of course, to get this result, it took decades, and it has been the work of many, many people. I'm just reporting the final, the latest determination and the final work by the White.
Isn't that the combination of many experiments? Or?
Very many experiments. I will show you right now. It's a combination of very many experiments, which of course have to be treated with additive corrections, which are therefore crucial because we are talking at less than 1%, right? So here additive corrections become crucial. And here are a pictorial view of the channels. You see, these are not even all of them, actually. These are some of the channels that enter. See, the 2 pi contribution is the main one. 2 pi contribution, plus or minus into pi is the leading contribution at this energy. And you see the cross-section plotted here as a function of energy, square root of S, you see it here. And this is the ratio, actually, of the cross-section divided by this quantity here. So as you can see, at below 1 GeV, the yellow curve, the yellow area dominates the contribution. So it's really the important part is really the pi cross-section, E plus E minus into pi. So that's what you have to measure very precisely. But then as soon as you go higher in energy, you see many other contributions, and this is pictorially very pretty to see all these channels. So you need to have really many, many measurements of different channels from different experiments at different energy range. So it's, of course, a really complicated business to put all this together. But in fact, this has been done for many, many years by many, many groups. And it, of course, the level of sophistication reached in this field is amazing.
Combine the errors to different experiments.
It's not easy at all. It's not easy at all. In fact, it's a lot of groups do this in very careful manners. Yes.
So may I ask questions? Simple question.
Yeah.
Hello?
Yes,
So
please go.
hi, I have some question.
Yes,
So in terms of, since you mentioned the hadron contribution, so in practice, the charmed mesons or the bottom mesons, those are also contributing, or that's really negligible up to this order?
No, everything has to be included, absolutely everything. And this is the list of channels. It's not even a full list, actually, of channels, but it's the most important ones. And it is plotted up to this energy, but just I chose this particular plot. But of course, you go up in energy. Then at a certain point, you will start trusting perturbative QCD, and then you can switch to perturbative QCD. And different groups actually use slightly different thresholds or use a region and then use perturbative QCD again. So it depends on the collaboration which threshold you use for perturbative QCD. But it's not certainly just up to 1.8, it's up to infinity, in fact, what you need. Of course, the weight will be less and less.
To rephrase my question in terms of G-2,
Yeah.
so the heavy mesons,
Yes.
such as charmed mesons or even
Yes.
heavier,
Yes.
in the loop, they will be very off mass shell, right? They are really not on mass. So it will be, as a resonance, it will be very much suppressed.
Yes.
So my question is, in the theoretical calculation,
Yes.
whether, so what you are saying is that all those contributions were included, even though it's small.
Yes, they are all included. And of course, the weight will be smaller and smaller as energy increases, but all contributions have to be included. And as I said, until you stop using data and you use theory.
Because I mean not only the low-lying modes, but if we go to the heavier mesons, there will be many excited resonance states and even some continuum states. In principle, you have to sum over all those things, and then there may be more bigger theoretical uncertainties, I'm afraid.
Yes, I'm sure. And in fact, there are uncertainties which are estimated, and they are part of this 40 that you saw before. So you see here there is an uncertainty 40 which takes into account all these issues that you are mentioning. But absolutely, I mean, the point is that fortunately, when you go to higher energies, the kernel is really, you can see it already here. It is most of the contribution, 3/4 of the contribution, you can see from the pie chart, is below 0.9 GeV. So all the details that we are talking about now, they are lying in this last little piece that you see up there, right? Above 1.4, 2, you see infinity is up there, right? So we are talking about very, I mean, the contribution have a weight. The weight function goes down with 1/s.
I see. So the numbers in the parentheses, those are all those theoretical uncertainties, essentially?
So I didn't understand, but or maybe I did, I don't know. So yes, the 40 takes into account all known uncertainties.
I see. Okay, thank you.
You're welcome.
How are we supposed to read the second pie chart?
The second pie chart is the error quadrature contribution. So this shows you that, for example, let's take again the 0.6, 0.9. This is the uncertainty coming from this particular.
So it means that 40 squared is equal to, so a fraction of 40
yes,
squared.
they are not the same number. So you have to compare. You should not really compare this number because this is from this paper 2018 and this is not. But okay, roughly, yes. The quantity squared, then because they added in quadrature, so that's why they are plotted error square.
Yeah, what is here is that if you measure this quantity, there will be statistical errors and there will be also systematic errors.
Absolutely, and there are several systematic errors here. For example, here there are errors due to the fact that two important measurements that you see here, maybe no, you don't really, because it's not precise enough in this plot. There are differences between, for example, in the pi channel, which is the most important one that you see here, the plus and minus into pi. There are differences, for example, between Chloe measurement and the Babar measurement. The Chloe measurement tends to be lower, the Babar measurement be higher. These differences have been included in the systematic evaluation, in the systematic error that you see here, in the 40 that you see here. So this, I would say, is from my understanding, is that this is a conservative estimate of the error, in the sense that it is many effects, all known effects have been included, and also these differences between the results have already been included in this error that you see here. Now, the problem is that the problem, or it depends on the point of view, there is an interesting, very important result that occurred in 2020. And it was the calculation, the first precise calculation at better than 1% precision of this contribution on the lattice. And this number is very precise, you see it here. An uncertainty of 55 in 10 to the minus 11. And as you see here, you see the comparison with the one that I showed you a moment ago. Let's call them the dispersive approach ones, the one that I just showed you a moment ago. So the dispersive one that I showed you a moment ago are here, and this is the value in this squared block here is the value from this collaboration, the BMW collaboration. So this result has been obtained on the lattice. You see, very, very precise. There were other results, of course, before, but this one is the first at this level of precision. And it's different. And it's clearly different. There is a tension of 2 or 2.5 sigmas, and it goes in the direction of the measurement of the G-2. You see here there is a blue band. This blue band, well, the central value here is the value of the hadronic contribution that you need to explain the experiment without new physics. Just without new physics. So this is the discrepancy that you have here. And this, on the contrary, is the value that you have if you use just the lattice result. So this is really puzzling because, of course, we should be talking about the very same thing. This is the leading order hadronic contribution to the muon g-2 obtained with data, and this is obtained with lattice. And as you see, they are different. And the second one goes towards the value chosen by the experiment, measured by the experiment in the assumption of no new physics. Now, this is really puzzling, of course, very puzzling. So we have no other full calculation of the lattice at this level of precision yet. But what we do have, and it's very recent development, this is a result of a window. So the lattice friends decided to choose a particular window in Euclidean time. And this window makes things easier for their calculation. So they all agreed on a window and they performed the calculation in this window. So it's not the full result, it's a part of the result, only it's a little less than half of the overall contribution. And they agreed on this window in order to study all together, all collaborations, that window, which is easier to compute than the full contribution. Because of course, first of all, they have to agree on that. And they do, and they really do. And this is the result you see. These are superseded, so let's forget about this one in gray, but look at the green ones, they are in very good agreement. And this is still the very recent results that we had just now. So you see—
Question?
Yes.
So in the lattice calculation, especially related to the hadronic contribution,
Yes.
Is it based on the fundamental Lagrangian on the lattice, and you are working on essentially all the path integral over the three-point function, or you are relying on some effective field theory?
No, it's the full, this is really lattice QCD.
So of the fundamental Lagrangian?
Yes, it is. Exactly. And there is, as I say, only one result obtained in this way, and it's the one that I showed you, the BMW result. But there are many other groups that manage, and you see it's here, BMW, but there are many other groups that manage in a particular window, so restricting to a particular window, to do the calculation as well, and several, you see them here, and they obtain the same result. So there is a partial confirmation of this result by the BMW collaboration. I say partial because we are really talking about a window only. But in that window, we now have, and this is really very recent news, we have this agreement, okay? So the situation here is, it's evolving. I mean, we have one single result, the BMW result on the lattice, which definitely reduced the discrepancy between the 4.2 sigma discrepancy that I showed you in the very first slide is greatly decreased. It goes to 1.6, if I remember correctly, standard deviation. So it's greatly reduced if you use this lattice result. Of course, this result from the BMW, the full result, has to be confirmed by other lattice calculation of the entire integral. Okay, for the moment, what we have is a check and a confirmation of the result in a particular window. Things are evolving very fast here. It's really amazing to see how much work is going on. And I mean, the result of the BMW collaboration has been an amazing result. I mean, this is a fantastic calculation. And when I worked on this, I've been working on the g-2 for several years now. And really, I could not imagine that they could reach such a precision, such an amazing precision already 2 years ago. This was really an amazing result. Now the point is that we absolutely need to have other collaborations to reach the same result and confirm or refute this result at the same level of precision. Because then we have to understand why there is a difference between this BMW result and the result from the data, from the hadronic data. They are really, they should be determining the very same thing, but the results are not the same. Okay, to make, this is already puzzling, of course, but to make the situation even more puzzling, if it's not puzzling enough for you, well, then there is a new result that appeared very recently, and this is a new measurement of the pi-pi cross-section. So the CMD3 collaboration at in Novosibirsk very recently published a new result of their E plus E minus cross-section. And the great surprise is that this measurement, that is from threshold, pi threshold, up to 1.2 GeV, is larger than all the previous measurements. And this is even more puzzling. So you see, this is a comparison of the green band that you see here is the CMD3 fit. And this is a comparison with the initial state radiation method. So the experiments like Chloe, Babar, Bess, and Peel. And as you see here, the green band, it's clearly higher. And this is a comparison of CMD3, again, the green band, with the data from also from Novosibirsk, but from previous collaboration, CMD2 and SND. So really a very, very complicated situation. We need confirmations here. Definitely need confirmation. This is yet another puzzle. So I should have put puzzles in the title of the talk today, because we are really have many.
So it seems to be really many error bars that are much smaller.
Yeah, much smaller. Yeah.
How can Chloe and Babar have in the lower part?
Much smaller. No, wait a second. Much smaller. You see them here. Look at the integral value that you see here. I didn't say correctly, sorry. Look at the integrated value that you see here. From 0.6 to 0.88, this is the CMD3 value, integrated to get that contribution to the muon-G-2. And you see, this is the error bar. It's not much more precise. No. Look at the Chloe combination here.
Yeah, exactly. But in the upper plots, the green band is really narrow, right? And the rest is kind of all over the place and has error bars.
Yes, but this is already the fit, the green one. It's already the fit. So I don't know how you would come. I mean,
how you can't really compare it.
Yeah, exactly. This is these are not points, the green ones.
Mm-hmm.
This is the fit of CMD3.
Okay,
yeah. It's not exactly there. What you can compare is in this figure here, and this is the integral of these quantities in the region 0.6, 0.88. So this region here, which is very important, of course. If you integrate in this region, you get this. And you see more or less, you had, as I told you, Babar was a bit higher, Chloe was lower, and now we have CMD3 that is much higher. Much higher means it goes in the direction of the G-2 experiment. Okay? Goes in towards the agreement with the G-2 experiment. But in disagreement with everything else. So, I mean, really puzzling. I'm going a bit slow. Let me speed up a little bit. There are higher order contributions. Yes, very quickly. I have the hadronic contribution. I will not go technical on this. Let me just tell you that these have been computed many years ago. They are smaller. You see the next to leading order vacuum polarization is -98. Negligible uncertainty, no problem here. We now have also expressions for the space-like region that can also be used for the lattice QCD community. So the lattice QCD community will also produce precise results for this contribution soon. And to do that, they need these kernels that are now available. And they will also be available for MUonE, which is a proposal for a new experiment at CERN, and I will talk about it in the last 5 minutes of my talk, or 10 if I go a bit faster. Then there is the next to leading order contribution. Here it is. And you see the number of diagrams, of course, increases. The contribution has been computed by Matthias Steinhauser and his group in 2014. It's larger than it was expected, 12, right? The previous one was about 100. This is only a factor of 10 less. So it is higher than, but still now it's known. So perfectly under control. Again, also for this one, together with Stefano Laporta and Lisa Balzani, we computed the kernels for the space-like region, which is, these are the kernels that are needed for the lattice community and the MUonE experiment that I will talk but tell you about at the end. So also this one can be computed over the lattice now with these kernels, and in the future, hopefully, by the MUonE experiment. this is the results that we obtain. Of course, you are next to next leading order, so it gets the expression are no longer so simple and neat as there is a kernel for one line. You know, the K function that you saw before was a simple line. Now, of course, it's getting complicated. To complete the discussion of the hadronic contribution, there is one last contribution that they will only, you can have a talk on this whole contribution here. It's called the light by light contribution. Many of you heard about it. It's a trouble life. Its sign even changed. It's a trouble life. Now everybody agrees it's positive. And the value that is quoted on the white paper is this one here, 92. With an uncertainty of 19 in 10 to the minus 11. Of course, this is an next leading order effect, like what we were talking before, right? So this is it's small. But there has been really a lot of work here. And if we are now confident about this, it's because there were many people, and you see them written here, who really took a step forward a few years ago by introducing the data-driven dispersive approach. So no models, data-driven approach, just like for the vacuum polarization. Of course, here it becomes much, much more complicated because you don't have a 2-point function, you now have a 4-point function, and you have to cut this 4-point function in all possible ways. But the recipe to do it was done already almost 10 years ago, and then the determinations were done using data for the most important parts. And this is the result that, in fact, has been obtained. And so the uncertainty is pretty solid here. Actually, it is solid. And even the lattice has done this calculation. And in fact, the result of the lattice, here they are in good agreement with this one here, obtained from data, phenomenology-based data. So we are in good standing here. We're really in good standing. Even the next to leading order contribution has been, we had a look at this term, we just gave an estimate. It's not a result, it's an estimate. In fact, you see it as a 50% uncertainty, but it's tiny, so we should not really worry about it.
But still, I mean, if you think about the final uncertainty of 16 or 17, this will have to improve, right?
Believe me that to get this 19, it was a lot of work. If we can get down to 10, I don't know. I'm not working on the light by light, but yeah, well, let's see what will be the progress, of course. But it was really an amazing amount of work to go down to 9. To reduce it a bit is probably easy. To go down by a factor 2, I don't know. I'm not an expert in this contribution. All right, if you put everything together, you have the 4.2 sigmas that I was telling you, but if you use instead the BMW 2021, instead of the white paper, it's only 1.6. So it's really difficult to say what is the standard model prediction right now because of the puzzles that I've been telling you. And it's really, we don't have one single number. And this is a problem, of course. Also because, as I told you at the very beginning, in a few months, we'll have the new number from Fermilab. It will have a reduced uncertainty. And okay, who knows if it will agree with the previous or not, but still, let's say it agrees. And then we have a very, very precise measurement from Fermilab. And then what do we conclude from this? So let me, instead of moving to a new area, which is how can we explain the discrepancy, I would like to tell you another point, which I found interesting over the time, and I worked on that a long time ago with Bill Marciano and Alberto Sealing, and then we redid this analysis much better in much more details in 2020. And this has to do with a question that we asked ourselves: can this discrepancy, the discrepancy between theory and standard model, be due to some missing contribution in the hadronic? Okay, some missing hadronic part of the hadronic cross-section. So the question is, can it be that some friends come tomorrow and tell us, look, we forgot a piece, or there was some missing part, some missing contribution in the hadronic cross-section. If you include it now, you go up to the value that you need. I say up because let me show you maybe once again this figure here. You see, we need to increase the hadronic contribution to match the measurement at Fermilab in the hypothesis of known physics, of course. Okay, so can it be that there is some missing hadronic contribution that brings these values up here? That was the question.
That would be some later on that.
Yes. Yes, some really just some, let's call it a mistake in the experiment. And that, of course, is a legitimate possibility that can happen. And we thought about it, in fact, many years ago with Bill Marciano and Alberto Sirling. And one thing we thought right away is yes, it's of course it's possible. If it happens, however, it will also have some repercussions somewhere else. And one place where it obviously will which will obviously be affected, is also the running of alpha. Because you see, this is the hadronic contribution to the g-2, the leading order one. And as I told you, it's an integral of the cross-section in plus and minus in two hadrons, multiplied by a weight function, a kernel function, that I told you earlier is this function k here. But the very same cross-section that enters here, the hadronic cross-section, also enters with a different weight, however, also enters in another integral that gives you the hadronic running of the fine structure constant. The difference is the weight function that you see written here. Okay. Now we are talking about low energy here, so essentially this is a constant. Well, this one, as I told you, roughly goes like 1/s. So it's a very different weight that you have in these two observables, but they use in these two quantities, but they use the same experimental input sigma that you see here. So of course, if you modify the cross-section tomorrow, and this fixes the g-2, well, then you will also change the running of alpha. Okay? The running of alpha is a crucial ingredient of the electroweak fit, the global electroweak fit. So how will things change in the electroweak fit if you do this fixing of the g-2 problem? Well, we decided to do it like this. Let's say that the cross-section changes wherever you want, at a certain point, square root of S0, and you change it in a certain bin of a size delta, and you change it, you just let this bin shift wherever you want and choose the width you want. So you just freely vary these two parameters. Now, what we thought back then there was no Higgs, right? It was 2008, so there were no Higgs mass prediction. So what we thought was, let's see how this would change the standard model prediction of the Higgs mass. You know, the standard model prediction of Higgs mass comes from the global fit. The global fit, the global electroweak fit, tells you what is the mass of the Higgs. And at the time, the upper bound, 95% confidence level upper bound on the mass of the Higgs was this value here, 150, 160 roughly GeV. Now, there was also a lower bound already at the time that was from Lab. Lab did not find it up to 114. So this was the window between these two. This was the allowed region in between. So our question was, if you fix the g-2 by changing the hadronic cross-section, how much do you change the global fit? And in particular, how much do you change the prediction of the Higgs mass? It changes like this. This black line here becomes this red line here. Meaning, it depends where you change the cross-section. If you change it at very low energy or at higher energy. In particular, this you see, this is square root of S, where you change the cross-section. Then, of course, you can change it in bins, wider, smaller, or just take a very narrow delta-like bin. It doesn't really matter. The message that we got back then was, you cannot change the cross-section at very high energy, because if you do change the cross-section at high energy, say above, I don't know, 2 GeV, above 2 GeV, if you do that, you fix the muon g-2 problem, but you introduce the problem somewhere else. You introduce the problem in the fact that the upper bound on the Higgs mass went below the left bound. So already back then, we could tell that this was not viable at high energy. Delta is the size of these steps that you see here. This is delta, this is another delta, and the red curve is obtained by taking the limit delta going to 0, which in the end gives you the whole, it's graphically easier to see. So as you see, this cannot happen at high energy, because as I said, if you do it at high energy, you will solve the muon g-2 problem, but you end up screwing up the electroweak fit. Now, this is the result we obtained back then. In the meanwhile, many things changed. In particular, we found the Higgs. The Higgs is here now, 125. So this analysis could refine very much so. Also, this was done using just a couple of predictions for the mass of the W and sin squared theta effective, the weak mixing angle. This was repeated doing a global fit. So after using all these observables that you see listed here for the global fit, there were also many theory improvements in the last 12 years. So this was from 2008 to 2020. this is what we obtained in 2020. Same thing, this is square root of S, so where you're changing the cross-section, where. Here is the Higgs at 125, is this blue line that you see here, blue dashed line up here, 125 is the Higgs mass. And this is the band of the prediction of the mass of the Higgs. So in orange is at 1 sigma, and in pink is at 95% confidence level. So as you see, if you change the cross-section above, well, if you look at the plot is 0.7, roughly 0.7. If you change the cross-section above 0.7 GeV, then the upper bound at 95% confidence level goes below the Higgs mass. So you start to have a tension. So roughly speaking, now 0.7 is at 95% confidence level. You can go to 3 sigmas and then it will become 1.2, 1.3 GeV. The message is, yes, you can change the cross-section, the hadronic cross-section to solve the G-2, but you can do it at low energy, because if you do it above roughly 1 GeV, then you have a conflict with the electroweak field. Okay, so this possibility exists, but it should be at low energy.
Suppose that that line would be just below 120. So suppose that you got a much narrower range, always below 120.
Yes.
How would you interpret that? That there are more wrong.
Yes, no, that's a very good point, Stefano, because already now there is a tension. Yeah. Yes, already now. By the way, sorry, this by the way does not. This was done in 2020. There was no CDF result. Okay, so if you put the CDF result, all this orange and pink goes down a lot. You know, you have 7 sigma discrepancy with that. So it's we didn't even plot it. It would be meaningless. It goes all the way down. It's already excluded by, I remember, I think it's 7 sigma. Well, from 7 it will go to 9, but it doesn't matter. It's already so excluded. So yes, you're right. There is already a tension here, driven mainly by the mass of the W, in fact. Mainly driven by the mass of the W.
So even without CDF, there is.
Oh yeah. It's well, the mass of the W has been going down with the years, which means that the Higgs prediction has been going up in the years, but not enough. So it's still low. Sin squared theta is pretty much fine. I mean, sin squared theta has its own problem, right? We know that there was the time when Lab had a result, SLC had another result in a different. If you remove all the essence, all the sin squared theta results, the upper bound becomes this dot dashed line. This is just driven by the mass of the W. So you see, the matter brings it even lower. So yes, there is already a tension to begin with. But if you touch the hadronic cross-section, it becomes worse. That's the message. But you're right, it already starts with a tension. Well, it's a tension, but notice that this is 1 sigma. Okay, so it's not a big deal. But still, yes, it starts already with a little bit of a tension. I will close this last part just mentioning, oh yeah, because otherwise it's really late. I will close by mentioning, okay, so you're telling me that in principle you could do changes, but only to fix the G-2, but only at low energy, right? Yes, at low energy. But how much would you need to change the cross-section at low energy? How much? What is the percentage? Well, the percentage is shown in this plot here, which shows the percentage shift of the hadronic cross-section when integrated in a range starting from threshold up to the value that you see here. For example, 1 GeV. If I integrate the cross-section from 0 to 1 GeV, I need to change the cross-section by roughly 5%. Is 5% a lot? Yes, it's really a lot. To give you an idea, this is in the same range, the uncertainty, integrated uncertainty of the hadronic cross-section. Integrated. So we are talking about big changes. If you touch so the message is, if you do it, if you want to touch the cross-section at high energy, you have a problem because you ruin up end up screwing up the electroweak field. Then you can do it at low energy. But at low energy, yes, you can do it, but there is no problem from the electroweak field, roughly speaking. But you have to change it a lot. Then you have then they have a conflict with what is quoted by the experimental precision of these results. Other papers in the same year that address the same issue. In particular, the first one is very similar. First and the last were very similar. They essentially, we are all in agreement on this point. I'm running late, so I just want to say, okay, let me say one word here. One word is, a year ago we thought, could it be that this puzzle, that which one is it? Because there are many puzzles now. Now the puzzle between lattice, BNW, and E plus E minus dispersive result, could it be fixed by new physics? Could it be that you have some new physics that enters in the measurement of the hadronic cross-section at low energy, such that you could explain this discrepancy? And you see, this is the result from E plus E minus into hadrons. This is the result from BMW, and this is the experimental value of G-2, the plot that I showed you already many times. Could it be that there is some new physics that brings this determination up here? Meaning, assuming that everything is correct, no mistakes in the measurements, but there is new physics hiding there, and you don't know, and therefore it should modify your result and bring it here. The short answer is no. We looked at this, and you would need sizable negative interference because it's the wrong sign, and this is excluded by a number of experimental constraints. So no, our conclusion is no. There is an exception that has been studied by these people. It doesn't involve actually the hadronic cross-section directly, but it involves the fact that you could have changed the E plus E minus or mu plus mu minus final state. You may have new physics changing the plus E minus or mu plus mu minus final state, and indirectly that would change the determination of the hadronic cross-section. It's a possibility. In the last 5 minutes, 8. Okay, in the last few minutes, let me tell you about this, because this is what, of course, I'm working on a lot in the last few years. And the MUonE project, together with friends Carlo Carloni Calam, Luca Tentadue, and Graziano Venanzoni. A few years ago, we were asking ourselves, but could it be that instead of measuring all these hadronic channels from many experiments in many different areas, can it be that we can actually do one single, clean, inclusive experiment that determines it all? And the answer is maybe yes, maybe yes. You see, this is the formula that has been, I've been showing you already more than once. It's the hadronic leading order, hadronic contribution, the hadronic cross-section sigma here, and the kernel function that I already told you a few times. Now, if you switch integrals here, you see, if you switch the integral over S and over X, you don't do, you see here, first we do the integral over X, and then you do the integral over S. But if vice versa, you do first the integral over S, you end up with this different formula. This different formula tells you that the leading hadronic contribution to muon G-2 can be obtained by knowing the running of alpha, okay? But at a value of Q squared that we called T, because it's negative. So in the space-like region. This formula is not ours. This formula was long known. It was done by Lauto, Peter, and Raffan in '72. But this was the formula that answered our question. Can you do an experiment that allows you to determine this contribution inclusively in one single clean experiment? So what we proposed was to really measure the leading hadronic contribution by a scattering data experiment. No, not E plus E minus into hadronic channels, scattering, Q squared negative, space-like experiment. So here it is, scattering of two particles. We thought E plus E minus at the beginning because we worked a lot on E plus E minus, and therefore we were driven by E plus E minus. And this is just a commercial. Look at the integrand in the two cases. This is the integrand for the time-like, the usual approach, and this is the integrand in the space-like. Yeah, if it's space-like, there are no resonances, right? So it's a smooth integral. The only problem is that you have to measure this very, very precisely. And now I show you how precisely. The idea is the following. The idea is measure muon on electrons, mu-e scattering. So mu-e into mu-e elastic scattering. Okay? And the idea is to, in fact, scatter muons on a target And we looked it up, and there is in fact a muon beam which has exactly the right energy that is needed for us, which is 150 GeV, roughly 150, 160, that's not important. And it's available at CERN right now in the North area. And then the idea is to put a fixed target that can be beryllium or carbon, and do a modular apparatus. You see, you shoot muons, you hit electrons, and out of this you get a muon and an electron here recorded. And what you need to do is to put several thin silicon strip detectors and measure very precisely these angles. If you scan the value of theta, the angle, you are scanning the value of q squared. So you're scanning the value of the q squared of the running of alpha. I remind you that the running of alpha enters here. See, running of alpha enters to this bubble that you have here in the T channel of this scattering. Okay, so this is this.
So in this way, you could scatter anything. So
Yes, but you need something very clean, right? So in fact, initially we got plus and minus. Sorry?
use muons and not electrons.
No, but muons on what?
No, what I mean is that you get that law
Yeah,
does not depend on the external factor.
yeah,
So
absolutely.
why you choose muons?
We thought muons because muons are very clean. So it's, well, you can do, as I said, also plus and minus. I mean, but so muons is very clean. It's a very, you know, they radiate little. Muons are very clean probes. And then, of course, it has to be on electron because you cannot make the target of muons. So, and in this case, also you have a leading order. You only have this channel here, right? So you don't have more than one channel. You have just one. That would not be actually a real problem because you can kinematically separate. But here you start from the cleanest configuration possible. A leading order, there is only one diagram, and this diagram, you see, muon electron. There is nothing else. There is no EE that would mix things, just electrons. It's just muons and electrons, and therefore you really start with one single diagram, and then of course at higher order they start mixing, but you start with the simplest configuration possible.
Minus, you also have to cross.
Yes, exactly. Yeah, exactly.
Just one question, what do you need several?
You need several. Yeah, that's a good point. You need several because in principle, you think you can just make one thick target, but then you have a lot of multiple scattering inside this this target. So you see, what we are thinking as targets of about 1 centimeter, which is already challenging because the multiple scattering is can be important. We need a precision which is incredible. Let me show you the precision that we need. One slide before the precision is it the right energy? Yes, it's the right energy because, let me go back to this integral here. This is an integral that we have to do. So you see integral over this variable x of 1 minus x times the function that we have to measure. Okay, so let me show you the product of 1 minus x and this function. Okay, we already know this function very well, of course. So let me show you this integrand, the product of these two. Integral from 0 to 1, okay, 0 to 1. Here it is. Integral from 0 to 1, and the integrand 1 minus x and delta alpha. The red curve is the integrand. So the area below the red curve is the hadronic contribution, the integral. Now, where is it peaked? It's peaked at this value of q squared, and this is 330 MeV. So if you have a machine that runs from up to 150 GeV, you can cover up to the blue line that you see here. Of course, not till 1, because 1 would be infinite energy. You need an infinite energy machine to reach 1. But if you have a machine of 150 GeV, you can go up to the blue line, which is, you cover a lot. And then you can actually determine the whole thing by extrapolating. But already the energy allows you to go up to here. There is another blue line here because we also need a normalization. It's unthinkable to do such a precision measurement as an absolute differential cross-section. What we can do is a ratio of cross-section, which of course helps dramatically in the dealing with the uncertainties, both theoretical and experimental. And the fact that we have a normalization region is really crucial. You see, there is a region here at small x, where delta alpha, this is just delta alpha alone without the 1 minus x, delta alpha alone is small. So if we actually go to this region here, our signal, for us the signal is delta alpha. That's what we want to measure. If we go to this region, delta alpha is very small, or better, the uncertainty of delta alpha is very small, to be precise, and therefore we can use it as a normalization region. So what we need to do is not an absolute measurement of the differential cross-section, but it's a measurement of the ratios of the differential cross-section. Otherwise, it would be completely impossible. It is still very, very hard because the precision we need is 10 parts per million. This is the estimate that we have. Let me tell you, from a statistical point of view, what we have at CERN right now, the beam that we have right now, with the details that are running, no news, I mean, this in running 2 or 3 years would give this integrated luminosity. And this integrated luminosity allows us to do an estimate of what we could reach from a statistical, purely statistical point of view, which is 0.3%. That is 20 in 10 to the minus 11. Okay, 20 in 10 to the minus 11 is better than anything that has been done for decades. I remind you that it's 40 now. Okay, so if you could do this from a purely statistical point of view, in a few years you could obtain an amazingly precise result. However, you have
It's with the square root of the
yeah, well, this is the statistical part. Yes, I would say.
If you want to put down the factor of 2, you just have to multiply times 4.
I would say so. I would say so. Probably yes, yes, but the problem is really not that. No, the problem is really the systematic effects, and this every day there is a new issue that we have to understand, and it's because this is 10 ppm, 10 to the minus 5. Is it doable? We don't know. CERN gave us the chance to do a test beam, so they gave us a beam to test the idea in 2017 and 18, and we wrote these 2 papers to summarize the results, and they look promising, they look good. Therefore, in 2019, we submitted a letter of intent to the SPSC panel at CERN, and it was approved for a test run, and the test run has been approved. So we had a test with a pull station and a calorimeter last October, and this year we'll have 3-week test run with 2, possibly 3, depending on the number of sensors that we are getting, because it's not so easy to get these sensors in this year. If things go well, then the idea is to write an experimental proposal, a real proposal for the experiment. And of course, there is a problem that we have the long shutdown of CERN, which will be in a few years. So it would be great to get at least a part of the experiment approved before that time and do a part of that before the long shutdown. This is a list of, as a theorist, I would be happy to talk for an hour about the progress we did, but I won't. But there has been a lot of work because you understand, we need a Monte Carlo at the level of 10 to the minus 5 for this scattering, okay, which is amazing, amazing. And we are certainly not there, but there's been a lot of progress there. You see, these are the papers that have been written since 2015 for the theory prediction of the MUE scattering cross-section. And it's really working. I mean, the progress is steady. Of course, we are not yet there. We need a full next leading order prediction and even higher summations. But what we have up to now is very promising. There are even ideas to study new physics, other different things from this experiment. And these were put forward by the papers that you see written here. Let me just show you a prototype in October of this is a station. You see, this is the target, this is the sensors. You see them 1, 2, and 3. The sensors, and the beam will go like this. Will go like this. And as theorists, we meet almost every year. We started in Padua in 2017. And then Mainz, MITP kindly hosted us in 2018 and will host us again in 2024 and did also this last year, and then Zurich in 2019. So we keep doing this workshop to really keep focused on the progress of the theory prediction that we need to finally build this Monte Carlo for this experiment at this level of precision. Here are my conclusions. I think that you will agree with me that there are some certainties, and one is that Fermilab confirmed Brookhaven. But already the fact that the discrepancy increased, yes, back then to 4.2 sigmas. But after that, there were developments. And the developments were the BMW lattice result, incredibly precise result on the lattice. It needs to be confirmed or refuted. There are now several lattice calculations that confirm BMW in the intermediate window. but we still need a confirmation of the full range. And then there is this new result for CMD3, which is larger. It's larger than all previous measurements. So yet another puzzle. I hope I convinced you that the discrepancy, the question that can the discrepancy be due to contribution in the cross-section, hadronic cross-section, missing contribution? The answer is yes, if at higher energy, not at low energy. And by higher, I mean above roughly 1 GeV, because otherwise you screw up the electrolytic field. And this is an important constraint that we should not touch. Now that there are all these puzzles, for sure, MUonE would be crucial, because MUonE would give a determination of the leading hadronic contribution to the muon G-2, independent, completely independent, and alternative to both lattice and dispersive one. So we really hope that MUonE will keep growing and fast enough. Okay, thank you.
Okay, thanks for Ernesto. So are there questions, comments?
I have some simple question. So
Yes, please.
when we calculate based on the standard model, is the neutrino contribution is also significant? Then in such case, we have some mixing angles and masses, some uncertainties. Are those also how big is it?
Oh, neutrino mixing. I don't know, but
my question is whether the neutrino mixing and those things are contributing to the G-2 calculation.
Oh, I never thought about it, as you say. The weak contribution, you see it here, of course, has a, the weak contribution here, of course, has a neutrino exchange here. But I mean, what could be the effect of the mixing here? I would say totally negligible, but I don't have a number. No, I don't.
So overall, this weak electric contribution is small.
Yeah, the weak contribution is 150 10 to the minus 11. Now we are talking at the variation induced by the neutrino mixing to this contribution. So I would say totally negligible, but I never thought of a number. It's a good point. I can think about it. I would say totally negligible. I mean, neutrino mixing here, but okay, I don't know.
Thank you.
Yeah, good point.
Any other questions?
In this scenario that you have missed some hadronic contribution.
Missing contribution? Yes.
You might just by telling the quantity that you need to fit alpha hadronic, the mass of the possible you have.
No, I'm not sure I understood. In the scenario where we touch the hadronic cross-section, say to fix the G-2, what is the question?
Yes, I mean, because you said that you may miss some hadronic contribution.
Yes.
Experimental. Is it possible to translate this into a hadron that you have not observed?
We can only talk about in terms of cross-section at a certain energy. That's all we can say. I mean, we can because that's all that enters in the dispersive integral. So in the dispersive integral, you have a function. This function is sigma. Now, what we are doing is that we are changing slightly this function. Why this is changing? We are not making any assumption. We are just seeing how much does it has to change, and so it doesn't matter which channel, so to speak, would it be. That is not that information is not entering in the because it's an integral. You only need to know how much it is, and by how much you have to change it. Of course, by the region, you can start to make your assumption. You can take your model, and then with your model, start discussing. But yes, but then it becomes a model. Now, we didn't assume at all. We just need to know how much the cross-section changes, and in which range. Yeah.
Thank you for
Please.
nice talk.
Thank you.
Very simple question. If the discrepancy between the electromagnetic is kind of value, it still exists even for the times of the big explain more new physics.
Yes, this is really a new talk, right? And, I think the day when the paper came out from Fermilab, if I don't remember wrong, the next day there were like 60 papers, 60 possibilities in one day. I mean, they were ready one day later. And of course, there were thousands before in that. Okay, one thing, in fact, we were chatting about this before, just before the talk, having coffee. Now, one thing, okay, let's start from this slide. This slide tells you that the discrepancy, if it's there, the discrepancy is more or less this. Let's look at the value. It's written here. The value is, sorry, here, 251 10 times to the minus 11. Okay, let's assume that this is the discrepancy and it is confirmed. Well, this looks very much like the weak contribution. See, the weak contribution, here it is 150 in 10 to the minus 11. Very similar contribution. Now, this was the driving thought for many, many years. Then, of course, so the idea was new physics is just around the corner and LHC will find it right away, and it is at the weak scale. Well, many things happened since the LHC turned on. And we don't have new physics yet. So, of course, people start thinking many other possibilities. Of course, you could have very light physics also. It doesn't have to be at the weak scale. I mean, you can have very light physics. And in fact, we're chatting about axion-like particles. ALPS can do the trick. And we worked, in fact, on that with Masiero, Paradisi, and Marciano. It could explain the discrepancy. It is certainly a viable options, but there are really very many others. I mean, some have been excluded in the time, but it's really very open. But let's say that I noticed a shift towards several light new physics examples in the last few years.
Questions? So actually, the MUonE experiment seems a kind of very nice solution in principle. And if you look at the picture, it seems a tabletop experiment. So if you look
yeah, but that's a long table.
It's not tabletop. So
it's a long table, 40 meters table.
Yeah, I'm just wondering, what is the budget?
Yeah, I'm a theorist, fortunately. So
you submitted some.
Yes. It depends very much how you count it. So to say the truth, I don't remember the exact values, but it's no longer such a small tabletop thing because you have to. Of
course, you have to produce a new one.
Yes, but even then, the problem is here it is. Here it is. So the sensors, it's a bit of a problem right now because they come from CMS. This will be the new CMS ones. And we need them now, and they will come later. So this is really at the stage where it's really only the beginning. Well, of course, there has been an enormous amount of work for CMS, but we really would like to have them now. And this is very sophisticated equipment. This is state of the art that we are having here. And then every day there is a new issue. How do you control the alignment? How do you control the temperature of the room? How do you... 10 to the minus 5 is an amazing precision. And therefore, there is really a lot of discussion about every single detail. At the end of these modules, they as I said, so this is we changed language. At the beginning, we call them modules. Now we call them stations. Because these things are called modules, and so we have to change our language. So now modules for us is where the sensor is, and station is the full box. They are roughly 1 meter each. We have to put 40 of them. So 40. So you understand that it's no longer really a tabletop experiment. This is just one. And the idea is to do this year another one, here it is. Oh, sorry. Here it is. See, we would like to have 2 stations, possibly 3 stations, because 3 stations means many sensors inside. It's not easy to do. And this is still very doable. Then the final goal is to have this 40, because that is what is needed to reach the statistics that they told you before. But we cannot think about that right now. It's too demanding in this. And so the next step really would be to have an intermediate situation in which we get down to 10 stations. So first we do the test with 2 or 3, and then we go to 10. Because if 2 or 3 works, then well, of course, there are many problems in scaling up, but it's a modular system, right? So we can really just put them together and see how they work with 10. 10 station would allow to do a measurement which is not competitive, neither with BMW, neither the lattice, nor with the dispersive, because it will not be sub%. It will be probably a few %. But honestly, it doesn't matter, because this would be a proof of principle that you can do a completely independent measurement with a completely independent technique at the level of a few %. If we manage to do that, then it's a matter of time, because then it's a matter of
comparing with, for instance,
yeah, look, I can show you. We can look at it here. Let me go back to this. Probably this one is the most useful for. Yes, here. This is 0.8%. Okay, so 1% would be like this. If you go to a few %, well, it would be these ones, for example. It's not enough to resolve the discrepancy. But considering that it's really such an important result, and considering the situation where we are, so really a puzzling situation, I think that to have an intermediate result would already be an important result. Clearly, the physics case will be coming at the end. It's for the case of it's for the result at the end. But it is such a new technique. I mean, if one thinks how much time it took for a plus minus to hadrons to get to this level of precision, it took decades, right, to get to this. And here we are running with a new technique at the level of 10 to the minus 5 precision in a very short time. So of course it's very demanding. And also we would need some more help. We would need some more people joining us, because it's really demanding, and it's a whole new world, and it's not yet an experiment, because as I say, it is a proposed experiment, so it is there is only a letter of intent for CERN. It's only an approved test run, but it's not an approved experiment. There is no collaboration yet, for example. So all these things make it a little bit complicated from a practical point of view. We hope soon to move to the level of being a collaboration, having a budget which is clear and identified, and then moving forward. We are still a little bit running to get things done.
Any other question?
So, what is the reason for using this kind of collision, like honest, stable, and instead of head-on collision?
Yeah.
Why this kind of scattering, like?
You mean why not doing doing like this center of mass instead of fixed target? No, we thought at the beginning to do a plus and minus, and it was just not possible to reach this level of precision with what we have nowadays. Because okay, we start thinking about the future and doing completely new things. Who knows? But with what was available, we thought about Chloe in Frascati. We thought, can we? Graziano worked for Chloe, so we immediately thought about Chloe. But to reach this precision in a collider was not thinkable for many reasons. But the one which, for example, you can imagine, there are the structure of the quadrupoles that are fixed for the beam. It doesn't allow all the good physics was in the beam fire. All the relevant physics was very forward, so we couldn't. We thought about Bell, of course, Bell 2. Bell 2 is actually for Bell 2 it was really too energetic, and because really there all the good physics was in the beam pipe. We thought of Chloe because Chloe was lower energy, 1 GeV, so it was not so much forward, it was more open, but then we had the problem of the quadrupoles. And so really practical issues that didn't allow to reach this precision. And so it's really so forward, and then we start thinking, maybe we should look back behind the target, then there is no issue of being forward or not. And that's when we thought about these targets. Of course, also we will not in a big target.
And what is the source of this incoming muon?
So the muons come from the SPS. So it's the same beam that gives the protons to the LHC. So the SPS, the LHC has many steps before reaching the LHC, and the last one is the SPS. It's a big ring. So the SPS typically sends also the beam to the LHC. But it can also shoot it straight towards the center of the LHC, where there is the north area, and there are these fixed target experiments. So these are beam lines. So the protons, it's a target. The targets produce pions. The pions decay in the negative.
So there is no uncertainty in the muon.
Yeah, there is an uncertainty. Yeah, that's a very good point. Yes, in fact, this is also being studied very much. There is uncertainties, of course, many uncertainties. One is the direction. Where does it come from? Because you think it's straight, but yeah, but you need to know it very precisely. But that is actually measured by the previous station, right? Because the previous station also has the thin detectors. So it is actually measured by the previous station, and then you know where it came from. Then there is the issue of, so this is the angular issue. Then there is the issue of the energy. Also the spread is important. But apparently this issue has been studied by my colleagues, and they claim that this can be kept under control. But of course, every day there is a new issue that they start thinking, because I'm a theorist, I'm not good at but they have every day a new thought, and almost every day a new solution, I have to say. So I'm really happy to see how this is evolving. Yeah, but that's a good point. There are many uncertainties also there.
Okay, any other question?
Yeah, so may I ask you some questions?
Yes.
Sure.
Yeah, so my query is that although this is not this part of this talk, so what is the status of this electron g-2 thing? So is it, so we had two results. One is discrepancy from standard model positive, and it is negative depending on the measurement of alpha. So how is the situation there? So is there any way to pin down at least in which direction the discrepancy is, not if not the actual value, at least the, can we test that which value is we can take more seriously? For example, why I'm saying this, because in the context of standard model, we know that the muon and the electrons both have very similar properties. And in the context of muon, we have a discrepancy is positive discrepancy, means the experimental value is larger than the standard model value. But whereas from the electron case, we have both values, and from simple extension of the standard model, it is very difficult to explain the negative discrepancy of the electron and the positive discrepancy of muon at the same time. So that's my question is that what is the situation? At least can we pin down the direction of the discrepancy for the case of electron?
No. The answer is no. We don't know.
Oh, okay.
It's as simple as that. The short answer, we have no idea. We have two measurements of alpha, and they are very different. They differ by 5.4, if I am not wrong, sigmas. So
yes,
completely different.
Yes.
One is on one side, and the other one is on the other side of what? Of the measurement by Gabrielse that he did in Harvard in 2008. And then just last year, he repeated with a much higher precision, and the new result that he obtained is right on top of the previous one. So it's an amazingly beautiful, it's a really fantastic result, this one by Gabrielse. In 2008 and 2022, he measured
Mhm.
The electron G-2, he got the same result with an uncertainty which the previous one was 2.8 in 10 to the minus 13. Okay, I'm talking about 10 to the minus 13 here. This new one is, I think, 1.3 in 10 to the minus 13. So unbelievable precision, and he got the same result. And so this is fantastic. Now again, however, we have a problem. We have a problem because where do we compare this? What do we compare it with? Well, we have two predictions, and these two predictions depends on the value of alpha that you use. And there are two experiments, one in Paris and one in Berkeley, as you said. And these two experiments differ by 5 sigma. So we really cannot say anything until this is settled, sadly. It would be great if it would be wonderful if they do fix it, this alpha, because for many reasons, but also because, as you said, the electron and the muon are cousins, right? So, in fact, I didn't talk about it, but in 2012, with Gian Giudice and Paide Paradisi, we wrote a paper, in fact, invoking the use of the electron G-2 to test for new physics. And not just to fix alpha, because the electron G-2 was used very often to fix alpha reversely, right? You think you measure G-2, you compare with the theory, and you extract alpha. And no, we thought maybe we can, if one has a value of alpha from experiment, then we can use the G-2, the electron, to test for new physics. And by the way, if you improve the precision a bit more, then you might be able to test if the same new physics that is perhaps showing in the muon is also showing in the electron. Because there are many classes of new physics where this corrections scaled, just like the naive scaling we called it, scaled by mu over mu quantity squared.
Yes, yes.
So you just scale that. And this, so if you take the discrepancy in the muon, the one that I showed you before, and you scale it by mu over mu squared, or mu over mu squared, so that you say, then you see that actually you need just a little improvement. But the theory is ready to see if the same discrepancy shows in the muon and in the electron in the assumption of naive scaling. But all of this is beautiful words, but we cannot do anything until we have one value of alpha, and we don't. So let's see. There is certainly a lot of pressure.
Part of this question, the question that was kind of, is there a direction that you
no, because they're really not in between, but so now the new value of Gabriel has, if I remember correctly, 3.9 sigmas on one side and 2 point something on the other side. So it's really a situation where you can't even say the sign, you cannot say anything. Unfortunately, no. You really have, we really first have to clarify the if you want, the atomic physics measurement, because measuring h over m, so h Planck constant over the mass, that's what they're measuring. And from that, once we have a value of alpha, which is in agreement, then we can start saying all the good things that we were saying before. But this is really a mandatory step that we need first.
Okay.
Yeah.
Okay. Thank you.
Sure.
Other questions? Okay, if there are no other questions, let's thank our speaker again. Yes.
Yeah, my name is Wanuli. I'm working here.
Nice to meet you.
Nice to meet you too.